Hi, my name is Itamar, and again, I'll be talking about what to do when your data doesn't fit in memory. But before I start talking about that, I just, as a prelude, wanted to remind everyone of the most important question you should be asking about any software project, which is whether that software project should be written at all. If the software you're writing hurts people, hurts the environment, the better you are at your job, the more damage you're doing. And so it's very important to ask this first. If you're working in a large organization, there's probably some employee group that's trying to push your organization in that direction. For example, I know Microsoft has a group called Microsoft Workers for Good. There's other groups in other large organizations. So for the rest of the talk, I'm assuming that you've asked yourself this question, you've said, yes, I'm not causing more damage to the world by writing the software. Okay, is this better? So the problem we'll be talking about for the rest of the talk is what to do when you have too much data. So you've written some code, it's analyzing some data, and when you load some test data, small amount, everything works fine. But then when you load the file with the real data, your program crashes. And so what's going on is you have, let's say, 16 gigabytes of RAM on your laptop. Your data file is 100 gigabytes of RAM. If you load more data than you have RAM, at some point you try to allocate some memory for the operating system. The operating system says, nope, sorry, we're out. And your program crashes, and what do you do next? So one solution is a big data cluster. And all you'll have to do is buy a whole bunch of computers. You spend a week setting it up. There's a decent chance you'll have to learn a completely new API. Not always, but often. And then if you're using a new API, you have to rewrite all of your code. And so this isn't a very appealing approach if you can avoid it. And so in many situations, there's a simpler, easier way. And I'm going to constrain the solution space to the case where you have a single computer, just like you usually do, minimal setup. I don't want you to have to spend hours and hours or days and days setting up a system. And for the most part, the ideal is that you should be able to use the existing libraries you're using, the existing code you're using. And it may be that you'll have to make some small changes. You do have this problem. But in many cases, you don't need a big data cluster. You can process all the data you need to on your own computer. And before we go to the solutions, it's worth asking, why do we need memory at all? Memory, RAM, is a thing that you can read and write to. Your hard drive is a thing that you can read and write to. So why does your computer have two completely different ways of storing data? And the one that's relevant to our purposes is that even solid-state hard drives, which are the newer hard drive technology, it's much faster than the old kind of hard drive, which would physically spin around. Even these newer, faster hard drives are much, much slower than your RAM, or something like 160 times slower. So if you were to try to do your computation without using RAM, just by reading and writing for disk, your data processing would be much, much slower, and it would probably take much longer than you're willing to take. And so we need to use RAM because RAM is the storage we have that lets you read and write data quickly. So the first solution, and in many ways the easiest, is to throw more money at the problem. So if I just went and priced out a workstation, 6-core CPU, 64 gigabytes of RAM, about $1,000. I didn't do any research. I didn't try to find cheaper deals. I'm sure you can get more memory for less money. But you can spend $1,000, and now you have a new machine with 64 gigabytes of RAM. I mean, if that's enough to fit your data in memory, you're done. You don't really have to listen to the rest of the talk. You can just go and run your program, and everything will work. Similarly, if buying is not an option, or you only need to run this computation once, you can go to your cloud vendor. This is a quote from Microsoft Azure, I believe. And they will have servers with a lot of RAM. So this example is 432 gigabytes of RAM, 64 cores, and it's $3.60 an hour. And so if you're only going to be running your computation for 4 hours, this is a great deal. You just spin up a new virtual machine, install your software, run it as normal, you're done. However, this is not always going to solve all of your problems. It may be that your data is so big that you can't realistically buy enough RAM in any shape or form to process it and fit it all in memory. It may also be that the cumulative costs of processing lots of data over time means that you really want to spend some time reducing your memory usage. So at one point, at one job, I did the calculation, and if we were to go into production with the compute time that we had at the time on the cloud machines, we would have spent all of our revenue paying our cloud vendor. None of it would have been left over for profit or for paying my salary. So I spent a bunch of time both reducing the computation time, but also reducing the memory usage a lot so we could run more data on a single machine. So if you can't add more RAM, the other solution is to use less RAM by writing some software. There are 3 techniques I'm going to be covering, and I'm going to talk about what they each mean in detail over the course of this talk. Just so you have a roadmap, the 3 techniques are compressing your data, processing your data in chunks, one chunk at a time, or maybe processing some of the chunks in parallel, and finally indexing your data so you only load the data that you actually care about. And for the rest of the talk, I'm going to be showing examples of how, both defining these techniques and showing examples how to use these techniques with 2 libraries, NumPy and Pandas. The techniques I'm showing are not exhaustive. There are other ways you can do this, both with NumPy and Pandas and with other libraries. And in addition, the particular structure of your data and the processing you're doing means that you might be able to do something specific to your data. So for example, it's often possible to come up with ways to compress your data that are particular to your particular data set. So this is not exhaustive. This is just a lot of examples so you can get started and so that you know what to look for when you're processing your data. And we'll start with compression. And compression is taking the same data and representing it with less memory. You can have lossless compression, where you have the exact same data, just stored in a different way. Or you can have lossy compression, where you're losing some details, but details that don't actually matter for your final results. And maybe you can drop a few of the details and no one will ever notice. You'll get the same basic results, so it doesn't matter. And when I say compression, you might be thinking of something like a zip file or gzip, where you have a compressed file on disk. That's not what I'm talking about, because those are ways to compress your data as it's stored on disk. When you load it into memory, you're going to uncompress that zip file. What I'm talking about is compressing the presentation once you've loaded the data into memory. And we'll start with NumPy. So in case you're not familiar, NumPy is a library in Python for processing arrays. You can do various operations on arrays, and each array has a data type. You can have an array of integers, you can have an array of floats, and integers come in different sizes. So you might have a 16-bit integer, where you can store values between 0 and about 65,000. You can have a 64-bit integer, where you can store values between 0 and a very large number. But 64-bit integers, while they let you store much larger numbers, they also correspondingly use more memory. So a 64-bit integer, as you would expect, uses 4 times as much memory than a 16-bit integer because it's using 4 times as many bits in RAM. What that means is, if your data can fit into a smaller data type, if you know that integers are never going to be higher than 65,000, you don't need 64-bit integers. 16-bit integers will do fine, and your memory usage will be cut by 75%. So let's see an example. I'm going to create an array. I can create 2 arrays. They're 2-dimensional arrays. Each one's 1024 by 1024. And the first array is an array of unsigned 64-bit integers. And the second array is an array of 16-bit unsigned integers. And we can look using the nbytes attribute at how much memory they're using. And as you would expect, the array that uses 64-bit integers uses 4 times as much memory as the 16-bit integer array. So if your numbers are no higher than 65,000, there's no point in using anything more than 16-bit, and you would just reduce your memory usage without changing any other part of your code except this one line. Another technique you can use is sparse arrays. Typically, if you're storing data in an array, you allocate a chunk of memory that basically maps one-to-one with the contents of the array. But oftentimes, your array is mostly going to be full of zeros. 0, 0, 0, 0. And occasionally, there'll be a little bit of data that's not 0. For example, if you think of a star map, much of the night sky will have nothing in it, and at some locations, there will be a star with maybe a brightness. And so why waste RAM, why waste memory storing all those zeros, where we can just say the default is 0, and we'll only store the information that's different than 0. And sparse is a library, this URL, that implements this idea, and it interoperates with NumPy APIs. It also supports a subset of the NumPy API, so you can often just swap it in depending on your interactions. And it has different representations of sparse arrays because depending on the structure of your data, there's different ways to compress it into a sparse array. And in this example, we'll be using a coordinate sparse array, where what it stores is the coordinate of where the values are different than 0. For example, you might say at x3, y400, there's value 3, and at x500, y2, there's a value 2.5. And so you can store, and if you think about stars, there's a reasonable way to store star locations. You store the xy location in your large image. And the rest of it is just presumed to be 0. So we create an array, 1024 by 1024. It's two-dimensional. And we're filling it with random values uniformly distributed between 0 and 1. Then we say anything that's less than 0.9, we're going to set to 0. This is an example from the sparse documentation, by the way, so you can find it there as well. And so what we're saying is this array is 90% zeros. Only 10% of it is not 0. So we can convert it into a sparse array. And if we compare the memory usage, as you would expect, the sparse array is using much less memory because it doesn't have to use lots of RAM to store all those zeros. And you can only use this technique if a significant amount of your data is zeros. And depending on the structure and shape of your data, you might need different sparse representations. Or maybe the sparse libraries representations aren't going to be good enough, and you'll have to come up with your own custom way of compressing that uses this basic idea. But you can save a lot of memory by not storing redundant information like all your zeros. So next, we're going to switch to pandas. Again, just in case you're not familiar, pandas stores what's called data frames, which are tables. And each column in the table has a particular type. So you can think of a CSV, where one column in the CSV is a string, another column is an integer, and so on. So when you load a CSV, pandas will make a guess about what the type of that column is. So if it sees that all the values in that CSV in a particular column are what looks like integers, it will say, oh, I bet this is an integer. And by default, it will use 64-bit integers to represent that column. So again, if we know that this column in this CSV is only going to have integer values that are no higher than 65,000, we don't need a 64-bit integer, we need a 16-bit integer. And so when we load the CSV, there's a way to tell pandas with a dtypes keyword argument saying, this column gets this dtype. It can also be useful if pandas is guessing wrong. In this case, we're just using it to reduce the memory usage. And so you can see if we just load the CSV, by default, this column uses around 40,000 bytes. But if we load it with a 16-bit integer as the dtype, as how much memory is used to store each value in the column, then it uses only a quarter as much memory. And it may be that we know that this is going to fit in 16-bit integers, so there's no point in wasting that memory. So again, just a one-line change. That was compression. And the next technique we're going to talk about is chunking. So chunking means we're going to load the data, but we're not going to load all of it into memory at once. We're going to operate on one chunk at a time and eventually process all the data that way. And so the basic intuition is maybe not most of the time, but much of the time, when you're processing your data, the processing you're doing doesn't require loading all the data at once. So if you think about finding the maximum value of an array, one thing you can do is you can load the whole array into memory, then find the maximum on that. Or you can split your array into two halves. You can find the maximum of the first half, find the maximum of the second half, and then the maximum of the whole array is the maximum of those two chunks. And so we didn't need to load, if we use this approach, we don't have to load the whole array into memory. We can just use parts of it, and we'll still get the correct answer, the maximum. And so if you're dealing with NumPy arrays, one way to be able to process your data in chunks is to use a library called ZAR, which is both a library and a storage format. And ZAR lets you store very large arrays on disk and then load only part of that array. And when you load only part of an array, only that part of the array is loaded into memory. And so you can load part of an array, you can read it, you might want to modify it and write it back, and then only that part needs to be written out. And so that allows you to very easily operate only on particular chunks of your very large array. So in this example, we are creating a one-dimensional array of length 1,000 with chunks on disk of length the array is length of 1 million, but it'll be stored in disk in chunks of 1,000. So if you load on these boundaries, it only has to load that chunk from disk. And then we're going to say the maximum of this array is the maximum of all the chunks, which we're going to load one by one. And we'll load a chunk, we'll figure out its maximum, and we'll have a list of the maxes of those chunks. And then we'll do the overall max of all the maxes of the chunks. So you can figure out the maximum without having to load the whole array into memory. And if you look at the type of the ZAR array object, it is a different type than a NumPy array. It's not actually an array. It's just a pointer to the storage on disk. You don't actually use any memory until you load a subslice, part of the array, into memory. And then you have a normal NumPy array, and you can run all your normal NumPy code. If you want, you can write it back to the ZAR. But when you load part of the array, you're only loading that particular part into memory. You don't have to worry about loading the whole giant array from disk into memory. Pandas also supports chunking, and in Pandas it's actually built in. You don't have to use an external library. So beforehand we saw how you can load a CSV, and if you load a CSV, the whole thing is loaded to memory and you get back a data frame. However, you can also tell Pandas to load your CSV in chunks. You tell it, I want a chunk size of 100. And that means instead of giving you one data frame, it'll give you an iterator of data frames, each one with 100 lines, 100 rows from your CSV. And so you can iterate over the result with a for loop. And each time, you'll get next 100 lines as a separate chunk. So you don't have to load the whole CSV into memory at the same time. So in this case, again, we're calculating a maximum. In this case, the maximum of one of the columns. And so we load each chunk, each one of only 100 rows at a time, and we figure out if the maximum of this chunk is bigger than the overall maximum we've calculated so far. And when we're done with our loop, we found the maximum of the whole column. And we've done it without having to load the whole CSV into memory. We've only loaded 100 lines at a time into memory. So now I'm going to go on a short digression, but a useful one. So we've been talking about processing your data in chunks. So you load 100 lines, figure out their maximum, load 100 lines, figure out their maximum. And if you think about it, calculating the maximum of chunk A and calculating the maximum of chunk B, those are completely distinct operations. Chunk A's calculation doesn't have to know anything at all about chunk B's calculation. At the same time, your computer probably has multiple CPUs, multiple cores. You can do calculations in parallel, and your computer will be able to handle it up to the number of cores your computer has. You saw earlier a virtual machine that had 64 cores, so you can do 64 operations in parallel. And so that means if we're already processing our data in chunks, we have the opportunity to process those chunks in parallel. And that won't reduce our memory usage, but it will allow us to run all of our calculations much faster in wall clock time, because instead of doing 100 lines at a time, we can do 400 lines at a time by doing 4 chunks in parallel on different CPUs. And one difference between normal operation we've been seeing so far and parallelism is that if you're doing multiple chunks in parallel, you need to shrink down your chunk size. So you can imagine that if you have 64 gigabytes of RAM, you can say, we'll leave aside 4 gigabytes of RAM just for the operating system and all the other stuff that's running, and we'll use 60 gigabytes of RAM to process our data. So if you're only processing one chunk at a time, you have up to 60 gigabytes of RAM with which to process each chunk. If, however, you're doing 4 chunks at a time in parallel, you're loading 4 times, you would be loading 4 times as much data at a time, and so you need to shrink your chunk size down accordingly. And so now each chunk can only have 15 gigabytes of RAM, and so you just have to use smaller chunks. Just something to think about when you're doing parallelism. And one easy way to do parallel computation is the Dask library. And I'm not going to go into much detail here. I'm just mentioning it and giving a couple of slides about it. Dask lets you run parallel computations on one computer. You can also scale it up to multiple computers. And you can just give it arbitrary Python code, but it also emulates the NumPy API. So you can write code that looks very much like normal NumPy code, and then tell Dask, OK, this is the code I want to run. Please do it in parallel for me using chunking behind the scenes. So we can compare these 2 bits of code. And one of them, I'm just opening a ZAR, and I'm running a maximum on it using NumPy. And that runs in about 1.1 seconds. And in the second example, I'm asking Dask to do the same thing. So I'm telling Dask, I'm going to ask you to load this ZAR and then run max on it. And now that I've told you what the computation is, please run that computation with 4 workers in parallel. And now it runs in 300 milliseconds, so about a quarter of the time, because we're using 4 workers. And it's only 1 or 2 extra lines of code. And once you're getting to more complex calculations, it's not quite as simple. But in many cases, Dask will let you very trivially take some NumPy code, have it run in parallel using chunks, and just get results back faster because your computer can utilize all of its cores. Similarly, Dask emulates the Pandas API. So you can take your Pandas code and tell Dask to run it in parallel using chunk processing and get faster results. So now that we're done with chunking, with a small aside about parallelism, we'll talk about a third technique, indexing. And indexing is used when you need to load a subset of the data. So imagine that you're reading a book, and you want to read only those parts of the book that are about aardvarks. So you could read the whole book from beginning to end and find all the mentions of aardvarks. Or you can go to the back of the book, where hopefully there's an index, look up aardvarks in the index, and it'll tell you aardvarks are mentioned on page 100 and 135. And then you only have to read those 2 pages. Excuse me. And so an index is a summary of the data telling you where to find the data that you care about. And it's usually much smaller than the overall data, so you can often fit it in memory, or at least it's faster to load from disk. And it allows you to only load the data that you are actually interested in. And since we talked about chunking before, and we're talking about indexing now, it's worth sort of emphasizing the difference between them. Chunking means loading all of the data. It's true that you're only loading part of it, but your goal is to eventually load all of the data, and you're just loading it chunk by chunk because you don't have enough memory. And so if you're asking the question, what's the longest word in this book? You are going to have to go through the whole book. There's no other solution. But you don't have to load the whole book into memory. You can load it page by page. Indexing allows you to answer questions where you know you only need part of the data. So how much money did we spend in July? You don't care about June, you don't care about February, you don't care about August, you only care about July. And so there's no point in loading any of the data from February. Now you don't technically need indexing. As you'll see in the following slide, you can just load all the data and then filter out everything that's not from July. That comes with its own set of problems. In practice, you'll often use indexing and chunking together. So imagine you've used indexing to only find the data for July. It may be that that data is still too big to fit in memory, at which point you might load it using chunking, loading it, let's say, 1 day at a time. So the simplest solution for chunking is a bunch of files in a directory. You are loading, you know that you're going to be loading data based on which month the data is from. So you just make a naming scheme where the data for a particular month has a particular name on the file system. And then your directory listing is basically your index. If you want the data for April, you load 2018-april.csv. And you don't have to load any of the data from the other months because they're in different files. So this is the simplest form of an index. Might be enough. But often you need something a bit more complicated than that. So let's take a look at an example. So I'm going to start with an example that doesn't use indexing, and then I'm going to rewrite it to use indexing. So the example is you are looking at voter registration records. You're running some sort of political campaign. You want to reach voters. And so you want to find which voters live on a particular street for your campaigning. And you're going to be running this query a lot because today you're campaigning in this neighborhood, so you need to load to these streets. Tomorrow you're campaigning in the next neighborhood, you have to learn you need to visit different streets. And so you're going to be running this query a lot. And so in our initial implementation, we load the whole CSV. And it's really big because it's New York voter registration records. There's a lot of people in New York. And so you can't load it all into memory, you're loading it in chunks. So we're going to load it, the Panda data frame, in chunks. And for each chunk, we're going to filter it down to only those rows where the street matches the street name we care about. And we're going to concatenate all those data frames and return them. And then we'll get a data frame that has all the rows where the street matches whatever street we care about. So that's how you would implement it with chunking without indexing. So next, we're going to see how we might implement this query only using an index. And because we're running this query a bunch of times, we're going to actually pre-process it a little bit to build the index. And we're going to store our data, instead of a CSV file, we're going to convert it into a database file. And in particular, we're going to use a SQLite database. Unlike something like Postgres or MySQL or Oracle database, the SQLite database is just a library. You can just import it into Python. It's built into Python. It just stores its data on a file. So it's operationally much easier to run. You're not running a server. You're just importing a library and running some code. but it's still actually a very powerful database. So we're going to create a database, and then we're going to load in our CSV and read it in chunks. And then as we load a chunk, we are going to tell Pandas, please write these rows to the database into the voters table, and if the table already exists, append these rows. So Pandas will automatically create the table in the SQLite database. You don't have to think about how it's going to be stored. I don't know what this table structure is. I just ran the code and Pandas did it for me. So you don't really have to think about very much how it's structured in the database. You're just having Pandas do all the work for you. Once you've loaded all the records into this database, into this file, you then tell the SQLite database, I want you to create an index on the voters table on the street column. And you can create multiple indexes. So if you end up running queries that require different columns in your table, you can create an index for that and get fast queries. You're not restricted to one index. And you can also do indexes across multiple columns, that sort of thing. And then we close our database. So now we have populated a SQLite database that has our voter registration records, and it has an index on the street column. And so now we can implement our function for getting the voters for a particular street. We open our database, and then we construct a SQL query saying, please load all the data, select star, from the voters table, where the street equals whatever value this function was called with. As an aside, this code has a SQL injection attack. You should not use normal string manipulation functions to create SQL queries. You should use something like the SQL alchemy library. I just did it this way so it's more readable. So you run this query, and you have this query, and then you tell Pandas, this SQL query, please run it against this database and give me the resulting data frame. So when you run the SQL query, SQLite is going to look at its index and say, if you're looking for 3rd Avenue, I know where in the database the records for 3rd Avenue are. I don't have to go through the whole database. I have this index that tells me where to find only the data you care about, and then it'll only give Pandas the data that results of that query. So we're only loading the rows we actually care about into memory. So now we can compare these two techniques. I'm using the Cambridge, Massachusetts voters registration records because I happen to have them. The memory usage is a little bit different than the two techniques. In the chunking technique, the memory usage was the 1,000 rows, the chunk size that we loaded for each chunk we loaded, plus the overall result that we returned. So if you found 10,000 records, then we have to store memory for the result. In the SQLite method, when we're using indexing, the amount of memory we had to use was the memory used to store the index. And again, we need memory allocated for the overall result of our query. In both cases, the index is going to be much smaller than the overall file. So I would expect in both cases, certainly with Cambridge, but even in New York, I would expect the index to be able to fit in memory just fine. And so we're not going to be running out of memory. So both of these techniques work in terms of reducing memory usage. However, the more dramatic difference is in the time it took to run the query. In the example where we used chunking, where we had to load the whole CSV, and then filter out every single row that didn't match our query, it took us 570 milliseconds. In the case where we had an index, where we only had to load the rows that exactly matched our query, it took 10 milliseconds. And so our query ran much, much faster because we weren't wasting time filtering out data we don't care about. So we've reduced our memory usage, but also because we have an index that helps us find things quickly, we've also reduced the time it takes to run the query. So those are our 3 techniques. So what if you're using some other library? If you're not using NumPys, not using Pandas, you'll be facing the same root causes. Memory is fast, so you need to do your computation in memory, but it's also expensive, so you may not be able to buy enough memory to fit all your data in memory. Disk is cheap. You can get enough disk space usually to fit all your data, but disk is slow, so you can't do your computation off your disk. And because you're facing the same underlying problems, you also have the same basic solutions, which are compression, chunking, maybe with parallelism if you can, and indexing. And now that you know about these 3 techniques, whenever you use a new database, whenever you use a new library, you know what to look for. You know, oh, I'm using too much memory. How can I compress it? Oh, I can't fit in memory. How can I load in chunks? Oh, I need to look up data, only a subset of data. How do I do an index? Those techniques will recur again and again in different libraries and technologies that you use. You should also not forget about the solution of just spending money. You might be able to just, your time is probably much more valuable than the amount of money it takes to buy a new computer. And so as a starting point, you should just go price out how much it would cost to buy a computer with more RAM. Or if you already have a workstation, it's easier to add memory to it than a laptop. And if you want to learn more, there are a number of talks at the conference that do deep dives into subsets of these topics. There's a talk about ZAR versus HDF5. HDF5 is a format a little bit similar to ZAR in that it lets you store large arrays, but it's also somewhat more flexible and more powerful. You can also use it with pandas. There's a talk about improving the efficiency of your big data application, which is about more sophisticated compression techniques than I've talked about here. And there's a talk about Dask, in particular using Dask with GPUs, but I think there's also a tutorial separately. But just, I think my guess is it's more broadly, you'll learn a little bit more about how to use Dask and what it does. Thank you for coming. You can find the slides for this talk at this URL, pythonspeed.com/PyData19. This is my email. This is my Twitter account. If you've enjoyed this talk, if you feel like you've learned something, I provide training. So if you think I can help your data scientists on your team improve their technical skills, please talk to me. And I think we have time for maybe 3 minutes of questions, and then afterwards I'll be outside.
So you haven't talked about the lossy compression, such as sampling or reduction of precision. Do you have some comments or advice for that?
So the question is, what can you do for lossy compression? And that's in many ways very domain specific, because what the data you're okay losing depends on the kind of data you're processing. I'm not really sure what lossy compression would be for a voter registration database. I guess you can filter out people who all live on the same address because you can only knock on one door. For images, you can think about JPEG compression, where you lose some of the details, but at least to the human eye, much of the time you won't notice a difference. And so in some cases, you can compress your data that way. When I was processing image data, I was considering a scheme where one part of the data would be stored with lossy compression of an image, and then the parts of the image that we knew were interesting would be stored with the original data, so we had the full amount of data. So you can also combine the two. But lossy compression is very specific to your domain and what details you know are not meaningful and that you can just drop.
So it sounds like with the indexing technique that you described, it's really useful when you refresh the data like earlier that day and then you run the query multiple times later, but not so much for like if you need to pull in the data like on the pin, right? Because then you still have to load in the data to the SQLite database and then query it, so all of that takes some time.
Yeah, so the question is it useful to, does indexing help you when you're processing data on the fly live?
Yeah.
Yeah, so indexing doesn't help you. The indexing is you have this unchanging data set you're doing multiple queries against. And so how do you efficiently load only parts of it into memory? Or load them with chunking. If you're processing data live, it's not going to help you. Okay, if you want to talk to me, that's my email, and I will be outside and maybe eating lunch.